inside the black hole that's as fast as possible out to Bob. And if Bob stays outside forever, he'll never be able to see that bit. But what Bob wants to do is he wants to stay outside long enough to see the Hawking radiation copy of that bit. And then quickly jump in and receive Alice's second copy and verify that this horrible thing, quantum zero-thing, has taken place. Okay, so why doesn't this work? It doesn't work because of a beautiful result by Page that you have to wait for half of the evaporation time of a black hole. This is quite general in maximally entangled systems. You look at a subsystem, and typically if you look at less than half of the system, it'll look like it's in a thermal density matrix. You get no information, even if the whole system isn't a pure state. You have to look at it at least half. A little bit more than half to get your first bit. You're going to arrange for that to be allocated if you have enough control over the measurement and if you know the estimate. So you have to wait that long. Okay, so Bob has to wait for half of the black hole to evaporate, measure the Hawking radiation version of Alice's bit, then jump in and try to see the other copy, and he fails by a lot. And this again, that's a calculation, I won't show it, but basically the point is that Bob soon hits the singularity no matter what he tries to do, and he has to receive Alice's bit before that happens. And because of enormous exponential redshift between Alice's inflow time and Bob's near the horizon, Alice has to send a signal with an exponentially large frequency. In other words, in a quantum whose mass is exponentially larger than that of the entire black hole. It's not even close to possible. Okay, so it's actually a little funny that we fail by this much, and it'd be more convincing if it was just barely impossible to keep both copies, and that's what Hale and Presto, they came up with a second strategy where you just barely fail. That to me made it much more convincing. I won't describe it in detail, but basically have a black hole that's already old, half of it has evaporated, Bob holds, has control over that early Hawking radiation, it's naturally entangled therefore with the black hole. Now Alice drops a bit in. Turns out the black hole basically returns to that bit immediately, limited only by the time that was scrambling or thermalization, mixing into all of the black hole's degrees of freedom. And then Bob gets it back quickly, jumps in, tries to see Alice's copy of the bit just as before. This time he misses the pair. Okay, so at first it seems that we have to choose between these two principles, inequality and the equivalence principle. But what these thought experiments show, when we look at it more carefully, we realize that there's another hidden assumption which we could give up instead. Omniscience. The idea that there has to be a consistent description of the entire global space-time. If we insist on that, yes, then there are two copies made from one, that's bad. But if we ask only about what any one observer can see, well, any one observer does not see one zero thing. And so complementarity is simply the decision to sacrifice three in order to preserve one and two. And so what are we saying more generally about this? I mean, it has to make something this radical that we're not allowed to think about space-time globally surely cannot be restricted to the context of just special solutions like asymptotic black holes. How would we draw a line? And so we have to have a statement that makes sense more broadly. Well, we can ask what is an experiment that we can actually do consistent with causality, but not, any practical limitations like the fact that you die or whatever. So then you consider a world line that as long as you can make it, so you stop it only when it hits the singularity or never. And you look at the past light form of the endpoint of that world line, the future light form of the starting point, that's called the causal diamond. And that denotes a region which is sometimes maximal. You can't probe anything that's larger than that causal diamond consistent with causality. Now, you have to have a theory for every such causal diamond, otherwise physics is somehow incomplete. So you don't need to have a theory for many of them put together, even if they have overlaps. That's more than asking for consistency for experiments that nobody can actually perform. And it looks like maybe that's where the problem lies here. So if you have a contradiction between different causal diamonds, Alice says that the information is inside the black hole, Bob says it's in the Hawking radiation. Too bad, they can't argue with each other. Everything, one means that each one of them has a consistent description with no obvious interpreted conflict. Okay. And as the thought experiments that I showed demonstrate, complementarity resolves the apparent paradoxes that people have exhibited until about 2 weeks ago. Okay, but now there's this very beautiful new thought experiment that Hans came up with, and we need to see whether complementarity resolves this. First, I need to tell you what it is. So here again, I don't display that well, but maybe you can see one thin black line going through the point B, that's Alice jumping into the black hole. That red thing here is her causal diamond, okay? All of this is the region that Alice could go. That blue thing here is the causal diamond of an observer who stays outside, Bob. And the overlap region, I think, purple percent, very low. And these black dots here, they're supposed to denote the early Hawking radiation. What we're doing here is we're waiting for the black hole, once again, to evaporate, just like in Presto again. We let it evaporate half of its mass. But it's still supposed to be big compared to, observer scales and Alice's size and so on. And so the early Hawking radiation, that more than 90% of whatever's already evaporated, that is maximally entangled with what remains of the black hole. Equivalently, it's maximally entangled with the remaining 10% that are still to come out of the black hole. So late Hawking radiation. Now, let's consider, we're not going to visit all of the late Hawking radiation for this argument, at least not for now. Let's consider one of the quanta in the 10% in the late Hawking radiation. Well, if the early radiation is maximally entangled with the late radiation, which it has to be because, we assume that the black hole is in a typical state where everything's maximally entangled, then it must in particular be entangled with this one quantum D. You can think of quantum, this one is sort of wave packet, typical Hawking wavelength, whatever the structural rate is. And we're going to focus on this quantum D, which is very visible up here and black. So now we're going to go back to this observer Alice, who falls into the black hole. And I'm going to arrange things so that Alice crosses the horizon when D is still close to the horizon. So I'm following the Hawking particle back to the horizon. Some distance much greater than the plane length away from the horizon that I have control, but I want it to be much smaller. The distance from the horizon, I want it to be much smaller than the structural radius away from the horizon, so that I can apply flat space intuition on the scale of this quantum. The scale is much larger than the scale of the next experiment on. So again, the idea here is that Alice and Bob stay together, wait for 90% of the black hole to evaporate. Then Alice jumps in, and I'm going to ask a question about one of those late quanta that haven't evaporated by the time she decided to jump in, but which is sort of on its way out to Bob as she crosses the horizon. So now, again, we can construct a contradiction. By the equivalence principle, Alice should see flat space physics on the scale much shorter than the structural radius near the horizon. But flat space physics maybe should be in the Minkowski vacuum. There's been no dramatic things happening. And as you know, in the Minkowski vacuum, just think of Rydberg space. You have some surface dividing Minkowski space. You think about modes that have support only on one side. Those are modes that go up the right of the Rindler wedge. Modes that have support only on the other side. You can write the Minkowski vacuum as a sum over product of such modes, highly entangled state. As a sum of the product of left and right modes. And so that's what the Minkowski vacuum is. Okay. So for Alice to see maximal, to see flat space physics, she has to see maximal entanglement between modes on the right and on the left of this dividing line. And D is a mode that's on the right, it's importantly on the right. So she has to see D maximally entangled with C. And recall, please, that we had already decided that D has to be maximally entangled with A according to Bob. And that's a contradiction. One can show, and one of the information people have shown us, that a system cannot be maximally entangled with two distinct other systems. Okay, both with A and with C. So that's a contradiction. So we must give up, it seems, either unitarity, the entanglement of D with A, that came from unitarity. Or one of field theory, I guess we could imagine that there's something that breaks down in evolving the talking quantum backwards and forwards from the near to the far, from the horizon region. Why? I mean, everything is way above the fine scale. Or the third option, we have to give up the entanglement of D with C. In other words, we have to give up the equivalence principle, and that's what Amps argued is the most conservative choice. But it's an extremely, even if it was the most conservative choice, it's an extremely radical conclusion. The lack of entanglement of short distance modes across the horizon implies a divergent stress center at the stress horizon. If you think of the Rindler vacuum, it's similar to being in the Rindler vacuum. When you compute the stress center, there's a sort of delta function singularity at the horizon. For any pure Rindler state that's around from and its collaborators. So what's going to happen to Alice if we give up the equivalence principle and say that there's no entanglement here? And, we can argue this with shorter and shorter wavelength modes. They all correspond to stuff that's later going to get out to Bob. So we're going to encounter singularity there. This is the firewall that Amps conclude has to be there. Alice isn't going to make it in. She's going to hit the firewall. Her description is actually going to be the same as the outside observer's description if you pry at the horizon. Something argues that nevertheless, you still need complementarity to resolve other paradoxes, and that's kind of interesting. The most obvious motivation for complementarity, namely the apparent conflict between the, just the description of the outside observer right at the horizon and the equivalence principle in negative light, that would have gone out the window, and nevertheless, you still need this principle for more subtle reasons. And that's one reason why it doesn't seem to be very important. But I think the most important reason is that giving up the equivalence principle seems like an extremely radical conclusion. So let's see if complementarity can resolve this paradox. So this is the work of Dan Harlow and my own work independently of each other. And I'll give you the upshot first, and the upshot is easy to convey by just drawing an analogy with the resolution of the zero-shifting paradox. It's here on the left. Here's the inside copy of psi, here's the outside copy of psi. Each observer, blue and red puzzle diamond, sees only one copy. The resolution of the firewall paradox is going to be that each observer sees only one entanglement. Here we have two incompatible entanglements. Each observer can actually only verify one. Let's see how that works out. So the infolding observer, Alice, well, people find it that the early Hawking radiation is consistent with unitarity. Those 90% everything is exactly as Bob's S matrix predicted. But notice, and this is a very central point, notice that Alice does not even in principle have access to the full S matrix. If Alice is going to be what we say she is, an infolding observer after 90% of the Hawking radiation, Alice is not going to see the remaining 10%. Alice does not have any operational way to verify the unitarity of the S matrix. It's a little bit confusing because, the first 90%, we're all consistent with unitarity, so it seems so natural to extrapolate and diffuse unitarity of the full S matrix and Alice's description of the universe. But complementarity is all about being really nitpicky about these things. And she doesn't see that she has no access to the remaining 10%. She does not get to use any electric properties those 10% have according to the different observers. Okay, so she can consistently assume, therefore, B doesn't have to be entangled with A, that B is entangled with C. Notice that there's a different theory for different infolding observers. It's quite consistent with what I told you earlier. Since different infolding observers, we call it up to 85 or 90 or 95% of the Hawking radiation, often have different causal values. There are alternative statements about what complementarity means that I think are somewhat misleading, like that there's a map between degrees of freedom on the inside, that there's some sort of scrambled version of the Hawking radiation. I think that's misleading, for example, it doesn't make sense to speak about all the degrees of freedom inside the black hole at the same time, according to the restrictions of law design. Nobody can see them all. Now, Bob has a different story. He came into the full S matrix, he controls the horizon between all. He has no reason to insist that he should be entangled with C. And so he can consistently say that there's no contradiction. He measures the S matrix is unitary, he's entangled with A, everything's fine. Each person sees one entanglement and not the other. Now, I oversimplified slightly. There's still some quantitative checks that one could do to see that this really works out. Alice, on her way in, for some time, still had a chance to send a message to Bob about quanta she encounters on the way in. In fact, she could just change her mind and decide not to fall in after she measures some of these quanta, accelerate really fast, stop and go back out. And so experiments, it turns out, up to 1 time before Alice's free-fall hits the horizon, those experiments have to agree between these two observers. So that seems problematic, because it seems like, this is what Dan said, it seems like Alice could measure the quantity needed to be not entangled with A, so that she later sees C and can find it entangled with B. But on the other hand, she could still turn around, in which case she should be entangled with A because she becomes an outside observer at the end and sees that unitary control. But in fact, there is no contradiction. Hollow has shown that Alice is just barely unable to. So what we imagine is that there's an earlier Hawking quantum that came in. It has to get at least far enough away from the horizon that Alice crosses it in more than one Planck time. That condition turns out to mean that Alice will not be able to receive a signal from some diffusional observer who hits this quantum at an earlier time inside the horizon and tries to send it over to Alice. It's the same, very similar contradiction to that on that decimal name for a different thought experiment. So the outcome here is that Alice can verify the entanglement on her way in. The entanglement of D with A isn't only if she can not verify the entanglement of D with C, and it works just there. It's the same timescale R log R that enters in this calculation. So again, there seems to be a conspiracy against somebody seeing both entanglements as that show. Okay, so I'm going to close by just saying that I have more arguments. I gave the one that's the cleanest, doesn't require any particular measurement from the Hawking radiation. It seems incredibly simple, and so at first there's very few loopholes. There are more complicated things you could try to do, but they also have more loopholes, and I'm sure that we'll be working on more thought experiments in the near future, and the discussion is far from over. Nevertheless, I believe that for now the equivalence principle remains safe. I believe the Armstrong experiment has shown us very clearly what complementarity means and does not mean. They'll probably won't agree with me right now, and again, I want to alert you to that. You should read their viewpoint, you should read their papers. But I think no matter how this plays out in the end, we will have learned something very important. Thank you.
Well, I think we'll have time only for one question while our next speaker gets ready. So let's go with the...
Yeah, it's a pity that we don't have more time, because I think there is some misconception going on in this when discussing these paradoxes. Because first of all, obviously, your treatment contradicts to Sever's thought yesterday. And the basic point is whether you are assuming, whether you are assuming that black holes, they carry air, you can measure what is the interior for an outside observer, or so on. So they carry what is the air. All these paradoxes are based on the assumption that for an outside observer it is fundamentally impossible to measure, to get any information from the inside of the black hole. And what we are saying is that that statement is wrong. The black holes, because it is not for the fact that all this time we are not thinking of black holes as large systems. Now, once you realize that black hole is a quantum mechanical large system, there is 1 over n probability to get information from quantum, which is trivial quantum mechanics at that point. Now, if there is information, if you can get information from the interior quantum mechanically, then obviously none of the paradoxes can appear, because then black hole is not any different than a box. It seems harder to open, because it's like a head back with infinity. Once you take n equals to infinity limit, that's the same as because obviously it becomes infinitely hard to open the box and get the information out. I think that there is a... Well, I think that no matter what we try to do, I think what's very robust is the choice that we are forced to make between these three, let's see if I can do this faster, between these 3 points. So I think that it's perfectly legitimate to explore all sorts of ideas. I suspect that yours fits into the second category of giving up the equivalence principle, but I think it's just important that there are these constraints, and they're derived by thinking about just basic principles of quantum mechanics and general relativity, and asking whether they break down. No, I'm not sort of starting from a conservative viewpoint and then finding that there's something about it that you have to give up. I don't think when I said that we have to give up the quantum principle, that's a proper misunderstanding. What I'm saying is that we have to treat black hole as a quantum mechanical system, realizing that it's the largest system in Hawking in some sense. After that, it becomes quantum mechanics, so you can measure the interior. You are all these things, you are working in the fictitious limit and going to infinity. It's not a fictitious limit, it's a limit when you have a black hole which is infinitely heavy. No, black hole is finite size. Of course, but n is finite size. No, n goes to infinity doesn't mean infinite size. That's probably the step.
Raphael said this is a discussion that will go on for a while.
It's a pity that we don't have more time, because
and so let's thank our speaker again.
Thank you very much. As the rest of the speakers, let me before starting to thank the organizers for the invitation to this very interesting and important conference. I'm very happy to be here. The title of my code is, as you can see from the transparency, black holes, and the quantum data.